Okay, hello, my name is Murrell. I am a student at San Jose City College, FMT, Facilities Maintenance Technology 104. Today is December 5th, 2018. My semester project, what I chose to do for my semester project was compare the operating frequency of two different fluorescent light ballasts. One is a magnetic ballast, and the other one is an electronic ballast. And the demonstration here, the takeaway that I want my viewers to see, is that the electronic ballast has a much higher frequency than the magnetic ballast. The electronic ballast can be anywhere from 20,000 all the way up to 70 or 80,000 kilohertz. In my case, if you were to come closer to the screen, you would see that this electronic ballast has an operating frequency of 71.43 kilohertz, okay? And the magnetic ballast, on the other hand, has an operating frequency of 60 hertz, just 60 hertz. So that's the same frequency that we would receive from the utility. So whatever's coming through the wall is 60 hertz. The magnetic ballast supplies to the light the 60 hertz frequency. The electronic ballast supplies to the light a frequency, in this case, of 71.5 kilohertz. So what you can see here, this top one is the magnetic. Okay, so you can see the sine wave there. And the bottom, because the frequency or the cycles per division is so high, it looks almost just like a solid line. But if we change the number of cycles per division, we will actually start to break that up a little bit, and you can actually see that there is an actual, what appears to be a square wave for the electronic ballast, which is displayed at the bottom of the screen here. Okay, so so that's kind of a visual representation that we got using the oscilloscope, and we can kind of play with it a little bit. And I don't like to play with it too much because I want it to be a nice, clear presentation. So that being said, before the presentation's over, part of my presentation is to do it on the oscilloscope, but then also to do it with the DVM here. So what I'm going to do, I'm going to go ahead and turn off my oscilloscope here without killing myself. Okay, so I'm going to disconnect the oscilloscope leads. Okay, and I do have a DVM here. I'm just going to move that a little bit. And the DVM will also, while it won't give me the exact same readings, it will be pretty darn close. So I currently have it hooked to the electronic ballast, and it is set to frequency here. And it does take a minute for it to appear. But if we just stand by patiently while I talk about something else, and I turn it on, which would be useful in this case, it will appear. So while we wait for that to appear, one of the things I do want to talk about, the electronic ballast is a lot more efficient. That means that you're getting a lot more efficient delivery of power. But not only is it more efficient, its efficacy, which I found during my research, is much higher. That means that per watt, because the frequency is so high, that per watt you're getting more light, so more lumens per watt. So not only is it more efficient, that is how much power is going to the light, the amount of light that you're getting per unit of power, or in this case per watt, is much higher than the magnetic. So the magnetic, that's why you can't find them at Home Depot, because they're nearly useless now compared to electronic ballast or LEDs, which are taking over the market. So if you were to come in closer, you would see that the magnetic ballast is pretty close to what we were showing on the oscilloscope. It's 66.8 kilohertz. So that's 66, almost 67,000 hertz. Okay.
No, that's the electronic.
This is the, yes, that is the electronic. If I misspoke before, I apologize. So this is the electronic with this 66.8 kilohertz. Okay, and then if I'm going to go ahead and switch to the other one. And this one is the magnetic. The first one, as I was corrected, was the electronic. Okay, I'm going to go ahead and attach that. And we've got almost exactly 60 hertz, which is the same frequency that's delivered from the utility. That's my project. Again, my name is Murrell, and that's it.